many modes of microgrids, different operating modes of microgrids. Then we will see the hierarchical control of microgrids. We see what are the challenges faced in microgrids by power engineers. Then we will see distributed energy resources and their control strategies. And we will see centralized and decentralized microgrids. And you see the structure and what are the main difference between them and what are their advantages and disadvantages of centralized and decentralized. And that means we compare the centralized and decentralized microgrids in some aspects. Then energy management. There is energy storage system and what are the advantages, what are their objectives, and all these things we will discuss. Then future directions in microgrid research. That is what at present what my PhD students are doing. I will just share some of their work. And last, you see the references. This is the outline of this contents now we are going to discuss in this session. So, my sincere appeal to all the participants: if you have any queries, please interrupt, no problem. And if you have any equal problem, please interrupt me. So, I'll correct it. Most probably, I am ready with, without any echo. So, we'll see. First, see what is the microgrid. We'll see what is the microgrid. So generally, microgrid is nowadays microgrid is a very hot topic, hot research topic for the researchers in different areas. It is not bound to only our electrical engineers. It is this area is open for communication, that is AC people, and as well as computer science people, that is IT people. Because microgrid is open research topic for all the engineers. It is a interrelated branch topic. So, but as a power engineer, as an electrical engineer, I will give a definition. So, group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that acts as a single controllable entity with respect to the grid. That is the exact definition of microgrid some textbooks. So that is a group of interconnected loads. It is not a conventional grid. It is a different grid. It is a micro. Micro means a small grid. What is the conventional grid compared to that? It is a very small one. So group of interconnected loads and distributed energy resources. Here the distributed energy resources nowadays we want to integrate all renewable resources like wind, solar, and other renewable sources. We want to omit all these conventional sources. So that's why microgrids plays very vital role. First is the definition group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that acts as a single controllable entity with respect to the grid. So that means the microgrid enables local power generation from local loads. It serves the local loads. It serves the local loads and comprises of very small generating power resources. So it is an integration of small generating power resources. So most of the generating stations nowadays are renewable sources like solar, wind, and fuel cells, all these things. So it is connected to both the local generating units and the utility grid, thus preventing power outage. That means in both the directions, that is the microgrid is most probably the microgrids are connected to the utility grid. Sometimes they are not at all connected to the microgrids. At the time, utility grid. At the time, this microgrid is called as island node. There is a two types of microgrid. Microgrid connected to utility grid, there is conventional grid, and another is microgrid in island mode. That means this is not all connected to the utility grid. Next, excess power can be sold to the utility grid. So the microgrid, if the loads are less as compared to generation of the microgrid can pump the power back to the utility grid. If it is connected to utility grid through changeover switch point of coupling point. So that means so if the surplus power is there, the microgrid can sold the power to the utility grid. So and size of the microgrid may range from housing loads to municipal loads. So this is very important. Nowadays, a lot of research work is going on this. So actually, usual microgrids are there for the serving purpose of a small loads. But nowadays the microgrid, there is a lot of research work is going on that the microgrid is upgraded to another. That means two or three or four microgrids they combine together another microgrid, and this microgrid is used to serve the purpose of a the area of the range of area is around 10 kilometers. Like I can say that municipal roads. So the lot of research work is going on towards this making the normal microgrids to serve the purpose of small loads into a big microgrid, and it's a combined microgrid so that has to be served the municipal loads. So the researchers, there is a lot of scope in the research in this research area, that is making the 3 or 4 microgrids into combined microgrid, and that microgrid has to serve the purpose of municipal loads. So we will discuss later. Next, we'll see what are the key attributes of microgrids. So just now we discussed the microgrid is a group of interconnected loads and distributed resources are able to operate in both island mode as well as grid control. Just now we discussed. So microgrid can operate in two modes. So one is grid connected mode and another one is island mode. So what is the difference between the grid connected mode and the island mode? We will discuss in detail later. So I'm not discussing now itself. So then act as a single control entity to the grid. So there is a single control. So control is very easy in there is a key attribute. These are the key attributes of microgrids. Then what is the need of microgrid? Why we have to choose microgrid? Already we have the conventional grid. So why we have to choose? Why we have to switch over to microgrids? Not only now, in future also, microgrid has a place. Microgrids will play a very vital role in the generating and as well as distribution scenario. So this the first one is the microgrid be the answer of the energy crisis, because we can serve the local loads by using of these renewable energy sources. So and that is the first one. Then transmission loss gets highly reduced. So this is very important. If you see the conventional grid, so the generating stations are very far away from the load stations, and this this power, the produced power or energy can be transferred from the generating stations to load stations via the transmission lines. So during this process, a lot of power is wasted. There is a lot of losses are there. So these losses are not at all present. I'm not saying not at all present. These losses are reduced in case of microgrid, because microgrids serves the purpose of local loads. That means the loads are within a clear defined electrical quantities. That is the definition itself saying within a clear defined electrical quantities of within an area of 1 or 2 kilometers, or sometimes it is very less. So the transmission losses gets highly reduced. Next one is microgrids results in substantial savings and reduces the emissions without major changes to life cycle. So microgrid results in it will give us gives savings because already we mentioned if the microgrid have the surplus energy, so this microgrid can if it is connected to utility grid, then we can sold the our generation to the government or distributed distribution companies. That means we can earn money from this if we have surplus. Then last one is a very important, provides high quality and reliable energy supply to critical loads. It's very important. So microgrids provides reliable energy, that is the trustable energy to supply critical loads. I will mention as here critical loads is the best example is hospital loads. For hospital loads, multi-specialty hospitals, we have to serve that. We have to provide us continuity of supply and quality of supply also, because there is ECG, lot of machines are there. They have to work without any interruption as well. Quality is also improved. So this can be addressed by using microgrids. So these are the needs that why we looking towards microgrid. So then that is about the just brief introduction of microgrid. Next, what is this picture clearly shows the difference between the traditional grid and as well as microgrid. If you see the picture, see this the left side that is violet color and the right side is green color. So the violet color, see, the way of communication is one way. So this is one of communication. So there are a lot of large power plants, that is conventional power plants, and so the centralized market is also centralized. That means no other competitors are there. So this is controlled by our government, and this is transmitted from long distance to the load through transmission lines. And at the end of transmission line, we know that the distribution system is there. Again, the distribution system is under the control of government. There is no competitors. And then here the consumers are passive. That means they have no authority. There are no active part in the system. So thus they have their main duty is to, or their main the main aim is to take the power. That is, they are passive. That's why I'm saying giving as passive. That means they will always seek the energy from the. This is only one-way communication. And if you see the microgrid, there is a feature that is always recent trends now. In the microgrid, if you see the group of renewable energy sources, most of them renewable energy sources, some conventional sources are there for backing purpose. So group of renewable sources comes together, to form one big generation or big power supplies. And here the market is decentralized, ignoring boundaries. So see, the market is not only governments or private companies or otherwise. We also can form the market, enter into the market, and this can be transmitted to the consumers through transmission lines. But these transmission lines, we cannot say it is a transmission line. Just it is a small lines to reach the consumers. And the consumer, see here, the consumer is active, participating in the system. If the consumer has a solar rooftop in his rooftop, so he can, if he has surplus energy, he can store his energy. Otherwise, if he has more than surplus energy, even though after storing, then he can pump back his energy to this microgrid. So this is this one. That means from this picture we can say that microgrid has two-way communication, and the traditional grid has only one-way communication. So that's why now the world wants to switch over from this traditional grid to microgrid. So that is just differences between the traditional grid and microgrid. Next, we will see what is the microgrid realities for India. So no power. First one is no power cuts. That means we want continuous supply. Then as reduces a lot of losses, transmission losses, and improves the quality of supply. Quality of supply also very important. Next, manage peak power, demand response, EV proliferation. That means peak powers can be managed by using the solar integration of solar cells, and then integrate renewable sources, distributed generations. That means integration of more number of renewable sources, and it's a way to omit reduce the conventional sources, renewable sources. Sorry, conventional sources. That means that is non-renewable sources. So this is that's why India. This is a priority of microgrid for India. So then we will see what are the components of microgrids. That is the brief introduction of microgrid and their advantages over traditional grid, and what are the priorities in India and microgrid. Then we will see the components of microgrid. What are the components of microgrid? So the first one is distributed generation. That is, we require distributed generations. Most of the time we went for the renewable sources like solar, wind. This is solar and wind and small hydro station. So this is sometimes we require this double power station also, but most of the time we don't. We are nowadays everyone wants to meet all these conventional energy sources. Next one is loads. First we will see the parts, then we will discuss each one by one. So then energy storage system. These are the main energy storage system plays very vital role. Energy management system, we can say energy management system. So we'll discuss this in very detail later. Next, MG central control. So MG central control is the heart of the microgrid. So MG central control decides it gives the balance between the generation and loads in the particular microgrid. We'll discuss later. Then power loss devices, that is converters, inverters. So then point of uncoupling. We discuss one by one. So this is a typical microgrid architecture. What in this we consider all the parts. See, this is a distributed generating units, and then here the loads are there. The loads again, the loads are critical loads and non-critical loads, and that is controllable, non-controllable. Here we classify as critical and non-critical loads, and then here we see the distributed generating stations are diesel, battery, flywheel, PV array, and as well as wind. So here you can see most of the generating stations are renewable sources. So distributed generation. Then if you see the first we see distributed generation. See, it consisting of wide range of prime mover technologies such as internal combustion engine, gas turbine, micro turbine, photovoltaic, fuel cell, and wind power. So these emerging technologies have lower emission and have the potential for low cost. It is low cost, and most of nowadays all these conventional, some of the conventionals are replaced with the renewable sources. So see here from this picture we can clearly say that distributed sources are most of out of four, not one, two, three, four, five out of five. Only one is renewable conventional source, conventional source, and remaining the renewable sources. So then next one is the loads. So loads are controllable or non-controllable. I can say these are controllable. These are controllable loads in this picture, and these are non-controllable loads. And again, these are critical and non-critical loads. Again, classified critical and non-critical loads. Critical loads are just now I mentioned critical loads are emergency loads. So you have to serve that loads. And then energy storage system. Definitely we require energy storage system. So the storage system is required for backing this microgrid, and then microgrid controller. So microgrid controller plays very vital role in the microgrid. So it manages the energy balance between the system and as well as loads. It is microgrid loads. It compares that every time it compares the total generation of these distributed resources and the load demand within the microgrid, and if it says that the generation is less than the loads, then it will shut down the non-critical loads, and it tries to give the supply to the critical loads, and vice versa. So this microgrid controller is a key player which will control, which will always see what is the energy provided and what is the energy required, and it simply I can say it balances the energy within the loads and as well as generation. So then power running devices such as here the power running devices or power converters. I am not going in depth. So it is made up of metal oxide, silicon feedback transistor, or IGBTs, or IGCTs, or gate term of thyristors, or triad. So whatever be the converters, their purpose is to maintain the voltage or frequency variations, so and converting AC to DC like that. So next we will see these are the parts just now we discussed. So microgrid are loads, controllable loads, non-controllable. Again, the controllable, non-controllable loads. Most of the microgrids will be connected to the grid, and they will be. And another thing is, sorry, I forgotten that. Another thing is, so this microgrids are already being mentioned that the microgrids are sometimes they are connected to utility grid, or sometimes they are island. So no matter which type of microgrid, definitely requires energy storage system. So that is energy storage system plays very key role in the microgrid. It gives the backup to the microgrid because nowadays most of the microgrid are integrated with the renewable sources, and renewable sources are intermittent. You know that renewable sources are not trusty working. So that's why we require an energy storage system, that is energy management system. Definitely we require an energy management system in the microgrid. So because whether it is connected, the microgrid is connected to utility grid or it is islanded, definitely it has to be backed up with energy storage system. Why we see in further topics. Then next one is the point of countability. We know that any microgrid, if it is converted to utility grid, it has to be converted at point of countability. That means we have to see the incoming microgrid voltage should be equal to the existing utility microgrid. Sorry, utility grid. Otherwise, there is a lot of problems will create. Then again, we have to address that, or sometimes it is the total system may shut down or damage. So to avoid this one, we have to go for that is one of the challenge we will discuss in the challenges topic. So I'm not going in depth now. Next, we will see the types of microgrids. Actually, the microgrids are two types only, but according to there's a power system applied. There are another two types also. There is a total four types of microgrids are there. So two key types of microgrids can be distributed, and two other related types of power system apply very similar technology. So there are first one is customer microgrids or pool microgrids. So these are the microgrids which are available now in the market. They are customer microgrids or pool microgrids. So we'll see this one later in depth later. So next one. First is the classification. Next, utility or community microgrids. Utility or community microgrids. So now, while I am discussing this one, while that is that is what is the need of microgrid. I discussed that nowadays 3 or 4 microgrids they form together. Another microgrid is a community microgrid. So we will discuss in detail that. Now, next one is virtual microgrids. The name itself indicates virtual. These are not at all till now. These are not at all available in the reality. Still, a lot of research is working going on. Next one is the remote power system. Actually, these are not a microgrid still, but we are treating as these are remote power system as microgrids. We will see one by one. First, we will see customer microgrid. See, this is a customer microgrid. This picture gives a practical view of customer microgrid. Customer microgrids are self-governed, and they are usually downstream of a single point of coupling. So many of the most well-known demonstrations now available in the market are customer microgrids. So they are practically easy to imagine because they fit neatly into our current technology. There is nowadays what we are seeing in the microgrids. They are customer microgrids. Just as a traditional customer has considerable leeway in the operation of the power system on its side of the meter. So the restriction on the nature of a microgrid are relatively loose. For this reason, one would expect much of the early deployment of microgrid technology. So simply, I can say these are the microgrid customer microgrids are the microgrids which are presently available in the market. So these are this is a picture which will show the customer microgrid. Then we will see the what is utility microgrid. See, this is a utility microgrid. So just now, while I am discussing about in the introduction section microgrids, nowadays microgrids they want to they want to enhance or they want to extend normal microgrids to serve the purpose of municipal loads. So this is that is called as utility microgrids or community microgrids. See this community get some lot of apartments are come together, they form one community. So in this lot of distributed energy sources and they come together, otherwise lot of 2 or 3 microgrids they come together and to form a big microgrid, and they will supply all this community. So that is a utility microgrids. Utility or community microgrids or milligrids involve a segment of the regulated grid. These are also existing well-known examples. So these are also existing well-known examples, but still this community area has to be improved. So a lot of research work is going on in the direction. So the utility microgrids, they form small microgrids that they come together, they form a big microgrid, and they will serve the purpose of this community. So then next one is the virtual microgrid. Virtual microgrids. So what is virtual microgrids? So virtual microgrids, these are still not at all present in the existing. So virtual microgrids cover distributed energy resources at multiple sites, but are coordinated such that they can be presented to the grid as a single control entity. So this is a virtual microgrid. See, they are far away from this distributed energy resources at multiple sites. See, multiple sites. These are all connected to through satellites or through virtual lines. So these are still not at all existing. Uh, so very few demonstration of virtual grids exist, but they have been proposed in the literature. Still, they are in testing mode. Still, they are not at all available. Note that to be consistent with the definition of the system must be able to operate as a control island or coordinate control island. So the virtual microgrids are still in the testing stage. They have not in existing ones. So these are the third category. Then fourth one. So remote grid. So this is a picture which clearly shows the remote grid. So remote power systems are obviously not able to operate grid connected. So we know that remote power systems are obviously not able to operate grid connected. So isolated power system involves similar technology and are closely related. So isolated power systems involve. So for example, this is a remote grid, remote power system where we operated PVs and wind at the remote area. So close that from research point of view, we can say these remote grids are also micro comes under the classification of microgrid. So then we will see this is a this is the total installed capacity of India. That is the power installed capacity of India in megawatts 13/11/2019. India is 3,65,980 megawatts. There and the bar chart contribution of each generating station, that is conventional generating station and renewable generating stations also there. See, obviously, you know that thermal power plants plays very vital role in the sharing of generating power. So thermal power plants is 63%. 63% of power from the thermal power plant, and then next one is the small hydro. Hydro power plant is very small, it's 1%, and nuclear also very small because of its limitations, that is the radiation effects. So the nuclear power plant is not trustworthy. Then hydro. So hydro is 12%. So it is also seasonal. So it will affect some monsoon. So if monsoon is there, then hydro power plant comes into the picture, and in summer hydro power plant is not at all trustworthy. So then wind power. Wind power is 10%, then bioenergy 3%, and solar is 9%. So there is a lot of research is going on to increase this wind and as well as this solar contribution towards the total generation. So this is about the installed capacity of power stations or the contribution in India as on 2019. So next we will see this is next we will see the modes of operation of microgrids. There are two modes of operation of microgrids that already we discussed. That is in our early stage. Again, we will discuss. That is just we discussed there. Now we discuss in detail. So there are two operating modes. This is a single line. This is a single line diagram of microgrid. See, this is a single line diagram of microgrid. This microgrid is backup with the distributed loads and as well as microgrid. This battery system. This is a battery system. Definitely, energy system is required. Energy management system is required for microgrid, whether it is connected to grid or whether it is island. So here, first we will see what is a microgrid, island microgrid as well as distributed. Sorry, grid connected mode. First one, if for example, this is a microgrid. The dotted line, you see the picture dotted line inside this is the microgrid. Consisting of microgrid already we according to our definition, it is a group of interconnected loads and distributed energy sources within a clearly defined electrical boundaries that acts as a single controllable entity with respect to the grid. So here, see the definition is according to definition. So there are different renewable energy sources: PVC panel system, wind turbine, and as well as UPS. And this battery system is there. Here, for conversion devices or power balance devices are there. So converting from DC to AC and here AC to AC for the same frequency like that. And this is a microgrid. If it is connected to, this is utility grid. This is a conventional grid. If it is connected to this microgrid is connected to this utility grid at point of coupling with static transfer chain switch, then this operation is called as microgrid is in integration with the grid connector. So then we can say that as grid connected microgrid. This operation is called as grid connected microgrid. That is, it is connected to utility grid. So and if this microgrid is because of some fault or otherwise if it is not at all connected to the utility grid, this is called as island mode. So there is that's why it is said if the grid failures island mode operation, grid connected to island mode operation, the switch off. So if it is a synchronization restoration, that means if switch is synchronized, then it is island mode is comes to grid connected. So this single line diagram is a one line diagram. It clearly gives the modes of the microgrids, that is grid connected mode and as well as island mode. So then we'll see this table gives the grid connected. So the microgrid operates in parallel with grid, and if it is grid connected, that means grid connected means if the microgrid is connected to the grid and it is parallelly operated with the grid and has ability to import and export to the grid in response to appropriate price signals. So import and export depending on the price signals. That means if the energy is more than if the energy produced in the microgrid is more than the loads which are connected to the microgrid, then the microgrid able to pump back the power to the utility grid. And while it is doing that, it will take care of the price signal. In MCC, microgrid central control will take care of that one. We will discuss that later. Next, this configuration requires a sophisticated controls, testing, and integration to manage interaction with the grid. It requires a lot of communications and as well as artificial intelligence is required for this grid connected. So a lot of challenges are there while we are connecting microgrid to utility grid. We have to address all these things. What are the challenges we will see later. Now then grid island mode. So no problem. It is not at all connected to utility grid. So in this mode, the microgrid controller can manipulate multiple distributed generation technology to achieve the appropriate power output to serve customer loads. That means its main aim is to grid island mode. It has to serve the loads, and the decisions will be taken by the microgrid itself, and it can also assist in system restoration effort during grid blackouts to allocate certain part of the grid. So island mode means if the switch is not at all connected to the microgrid is not at all connected to the main grid, that is called as island mode. Island mode has its own benefits. So this is this picture. The single line diagram which clearly shows the properties of grid connected mode. What is island mode? See in this C, there are different feeders of the feeder A, feeder B, feeder C, and feeder D. Out of this, feeder A, B, C are served by the microgrid, and feeder D is served by the utility grid. So this microgrid is connected to the utility grid. Here I have not shown the utility grid. Just point of common coupling I have shown. That means here the microgrid is connected to the utility grid via this point of common coupling through static switch. Closed. If the switch is closed, this microgrid is in grid operation. That is grid operation mode. At the time, the microgrid serves the loads to this, and this feeder is supplied by this one. For example, if something happened, otherwise, if this switch is open, at the time. What will happen? This feeder is open means this is not at all connected to this one. So something happened here. So this feeder B is not at all supplied by this microgrid. Only this microgrid supply its own feeders, own loads within the clearly defined boundaries. So that means feeder A, feeder B, feeder C will be served from the microgrid. So this mode is called as island mode. So I think this picture clearly gives the grid connected mode as well as island mode. Next, what are the we'll see what are the importance and benefits of microgrid. So first one is it enables moderation of the grid. So that means a lot of communication and as well as different latest technologies are introduced in the system. Next one, it enhances the integration of distributed and renewable energy sources to meet the end user needs. Simply, I can say, I don't want to discuss much more here. Simply, I can say, nowadays all these conventional energy sources are replaced with the renewable energy sources with the help of microgrids. It is integration of much more renewable energy sources to the grid to serve the purpose of our loads. Next one, it provides support and backup for main grid. Yeah. It provides the support and backup for main grids. For example, if something happens, main grid has some problems, then the local loads can be served from the microgrids. Next one, smart control of energy demand and increase the power quality. Obviously, a lot of communications and new technologies and computer programming and applications, computer programming as well as a lot of these automation techniques comes into the picture in MCC. So obviously, we get a smart control of energy and improves the power quality. Next one is reduces the emitting of greenhouse gases. Definitely, because our main goal is to we have to switch over from conventional energy sources to renewable energy sources via microgrids. So that's why the greenhouse gases will reduce. Next, that is about the benefits. Then we will see the hierarchical control for microgrids. In regard to the architecture of microgrid, there are two different approaches that can be identified as centralized and decentralized. First, we will go centralized and decentralized in just we will discuss, and later we will go in detail, and later finally we will go for the comparison between the centralized and the decentralized and distributed control. So if you see the centralized control, it requires a lot of sophisticated techniques and a lot of communication channels and a lot of other high-end computer systems are required to analyze the large amount of information. That means at every time it has to take the it has to collect the data from the loads, and from that it has to be processed. That means it requires a lot of energy, a lot of data analysis. So centralized control has its own limitations. So it requires a high sophisticated and high end communication channels. Then in a decentralized control, each unit is controlled by its local controllers. That is without knowing the situation of others. A compromise between those two extreme control schemes can be achieved by means of a hierarchical control. So that means decentralized controller, the local controllers are local loads are served by this decentralized control, and the controlling actions can be taken by its own without in a simple manner. But we have to achieve a compromise solution between these two controllers. Hello, is it my voice is audible? Hello? Yeah, because echo is still going on, no? Okay. Okay. So yeah, if meanwhile in between the supply is gone, please call me, madam, because here our power is shut down. I am running with my UPS. Okay, so hope so. Okay, so on the other hand, that means we want the compromise solution between centralized control and decentralized control. So that's why we required hierarchical scheme. So in the hierarchical scheme, there are three levels. There is primary level control, secondary level control, and tertiary level control. So in this diagram clearly shows the hierarchical control. That is primary level control. This is the primary level control, and this is secondary level control, and this is a tertiary level control. So in this we will see one by one. So the primary level control, primary level performs the control of local power, voltage and current. That is the primary level. Its purpose is to control the local superposition. That is voltage, and it will control the voltage and current control, and as well as it takes about the power sharing control. It takes about the power sharing control. Then the primary level control always takes the command from the secondary level control. So always takes the command from the secondary level control. Now that is the main purpose of primary level control. The primary level control main purpose is to control the local to take care of the local supervision and that means it controls the voltage and current control, and as well as it takes the power sharing between the loads and as well as generating units. And next one is the secondary level control. So in the existing hierarchy level, it is top of the layer on a primary level. So it deals with the power quality control, such as voltage or frequency restoration, voltage unbalance, and uh, harmonic compensation. That is the main aim of secondary level control. Secondary level control, that means it take care of the power quality control, and it also performs the synchronization and power exchange with the main grid. So it's also another aim of this one is synchronization control. That is, it takes care of the synchronization and power exchange with the main grid or other microgrids. Next one is a tertiary level. So this is tertiary level is very important. Conventionally, tertiary control is issued with the task for managing power flow between it is a power flow between microgrid and external grid. Microgrid and external grid. That means it manages the power flow between microgrid and as well as external grid. So in recent days, the aim of tertiary control is to introduce intelligence in the whole system. So we can introduce the intelligence AI techniques in the tertiary level. So the tertiary control will attempt to optimize the microgrid operation based on merits of interest, most efficiency and economics. So that is what I mean to say is from the knowledge of from both and microgrid side and as well as external grid, so are essential for this tertiary control. They have to be processed, and here we can use the optimization function or optimization techniques to obtain the economic dispatch in right manner. That means information and communication technology plays very vital role in this tertiary level control. That from that we have to collect the data, and we can use the optimization algorithms. We can employ the optimization algorithms to process this gathered information and to give appropriate decisions. So that means tertiary level control is the level where we can introduce artificial intelligence and other optimization techniques, such that we have to process the data with, and we have to form the problems, and that problems we have to use our own optimization techniques or algorithms, such that we have to give appropriate decisions. From that, the second level and as well as primary level can be controlled. So this is the hierarchical control scheme. It will use the compromise solution between the centralized and decentralized microgrids. So that is about the hierarchical control scheme of microgrid. Then we will see what are the challenges in microgrid control and management. So what are the challenges? So in future flexible distribution system includes a lot of microgrids are incorporated for economic operation and distribution system. So regarding the control and management aspects, the following issues takes place. We have to address. That is, the following challenges are addressed in the microgrid control. So we will see one by one. First, we will see voltage and current control. This is one of the challenges in microgrid. So the islanding operation requires some of the distributed generators providing voltage support to the isolated system, and some of the DGs injecting power following certain references. That means proper voltage and current control schemes need to be developed and applied for operating each single unit. That means voltage and current control has to be addressed with the proper voltage and current control schemes. That is a requirement of design of voltage and proper voltage and current control schemes are required to address this challenge. Then next one is a power sharing control. So although distributed fashion of generation and consumption enhance the efficiency of the entire system. So power sharing among DGs becomes critical issues. That means which DG has to be loaded up to its maximum and which DG has to be loaded for its normal. That means we have to see its economy also. That means since if one DG is to be overloaded as compared to other, the total entire system may trip or offline or it may shut down. So we have to take care of the optimal loading of these DGs with the help of this optimization techniques of microgrid central control. That means we have to address this. Otherwise, the total system may collapse or may trip. Next one is we require coordination between the different DGs. So DGs can be generally classified into three categories. Just already we discussed, including conventional generators, that is fossil fuel power generators. Next, energy storage system. That is already I mentioned, energy storage system plays very vital role, important role in the microgrid or otherwise smart grid, microgrid and as well as smart grid analysis nowadays. Here energy storage system, that is batteries, flywheel, supercapacitors, flow batteries, supermagnetic materials, capacitor. So these are the batteries, energy storage systems, and another one is renewable energy sources. So that is photovoltaic panel, wind turbine, hydropower, etc. etc. These we require the coordination among all these things. Otherwise, that means we have to address this problem. That is the best coordination has to be obtained with respect to security and stability. Otherwise, it is for example, if you are not coordinating, if you are not calculating the each DC's output cost of the DC's there, without knowing that we have just our aim is to supply the power only, then it is possible that must be required revenues also in the, because microgrids we are investing a lot of money, so we require revenues also. So that's why coordination on the deals also very important aspects. Next one is academic dispatch and optimization. So this in this area, my PhD students are working. Two regular PhD students are working in this area. So optimization technique, that is academic dispatch and optimization. So the optimal operation of the system demands pertinent mathematical representation of the system, appropriate formulation of optimization problem, and besides a powerful and suitable algorithm. So that means we require a suitable, we have to choose a suitable and powerful algorithm such that the academic dispatch takes place in a smooth way. However, with the condition of renewable energy and the active participation of consumer sides, generation and consumption uncertainties have to be taken into consideration. So we have to take all this consideration. That means we have to address this also. So if any researchers who or otherwise any faculty members, those who are doing wants to do PhD in part time, so or in a, that is what we can say, not full time, that is part time. So this area has a lot of objectives. I will give the objectives at the end of my session, what students are doing. So that means this is one of the most promisable research area for the researchers who are interested to do. So it is optimization of this academic dispatching and optimization. He will be required to process the data, and we have to choose the accurate or powerful suitable algorithm. So then next one is the power quality issues. So we have to address the power quality issues. That is deteriorated power quality, such as voltage imbalances and harmonics due to existence of unbalanced or electric loads, may cause abnormal operation of sensitivity equipment, so incur additional power losses and affect system stability. So that means we have to address this power quality issues with the design of appropriate filters and selection of converter topology and drivers and advanced control methods to realize multifunctional control. So that means we have to address all these power quality issues with the help of latest technology. So that is about the challenges what we faced in the microgrids and how we can overcome this in a brief manner. I explain. So, but each one is its own research objective. That is voltage and current control is one research objective, and power sharing control is another research objective. This is a coordination between different sort of DGs is also another, that is optimal location of DGs and optimal uh, active participants of the DGs also another subjective, and economic dispatching and optimization is one of the research objective. And at present, my regular PhD students are doing this. They published two papers in this optimal dispatching, that is economic dispatching and optimization. Then power quality issues. So power quality issues is another sort of there is an objective for researchers to do something in this area. Next one is we will see the distributed energy resources. So distributed energy resources, just now I mentioned the distributed energy resources is a combination of conventional as well as renewable sources. So the DG units are usually connected at either medium or low voltage levels to the force microgrid. So figure 3 shows a DG unit comprising a primary energy sources. Primary energy source here, I can say this energy sources it may be renewable or it may be conventional. So and here interface medium, definitely interface medium is the converters and the switchgear at the unit point of coupling. So this is a point of coupling switchgear is required. There is a this CT, PT, and all these things are switchgear uses grid connection. So point of coupling by CT, and this is a control protection and this is a monitoring. So this is a black diagram representation of DC unit of a microgrid. So in conventional DC unit, if it is a conventional DC unit, there is a synchronous generator driven by a reciprocating engine or an induction generator driven by a fixed speed wind turbine as a rotating machine. So converts the primary energy source for the purpose is to convert the power from the primary energy source to the electric power. The main aim is to generate the electric power. So also acts as the interface medium between the source and the microgrids. Between the source and microgrid, it is the interface medium. Is the interface medium for electronically coupled DC. So as just now I mentioned, this is a converter and can provide another layer of conversion and control. Example, voltage and frequency control. That means interface unit here it can control the voltage and as well as frequency. So and acts as the interface medium with the microgrid. The input power to the inverter. So interface inverter from the source side can be a AC or a fixed or variable frequency or DC. So here this is a control for protection and monitoring. Every time it monitors, and this is a closed loop one. So this is a distributed energy resources of a microgrid. And next one is DER control. Distributed energy controls. So what are the DER controls? Control strategies for DER units within a microgrid are selected based on the required functions and possible operational scenarios. So we have to choose the requirements functions within the possible operational scenarios. So these controls of DER units are also determined by the nature of its interactions with the system and other DER units. Here the main control functions for DER units are voltage and frequency control, or active or reactive power control. So that means here there are two control. We will see the voltage and frequency control, how their controls utilize, and active and reactive power control. So here the table the table provides the general category of the major control functions of DER unit and divides the strategies into the grid following and grid forming control. There are two controls: grid following and grid forming control. So each category is further divided into non-interactive control method and interactive control method. See, out of this we will discuss about the grid following approach. So in this, the table gives the classification of control strategies for electronically coupled DER units. So in this grid following control and grid forming control, Again, they are further classified into non-interactive control method and interactive control method. So in that, in the grid following control, non-interactive control method, power export with and without MPPT, and grid forming control, non-interactive control method, the voltage and frequency control on it take care. Then in interactive control method, in grid following control, it will take care of power dispatch, that is real and reactive power support. And here in grid forming control, it is take care of the load sharing control. Next one is we'll see the grid following power export control. So grid following power export control strategy is often used to control the DER output power within the voltage and frequency limits as determined by the microcontroller. So first we will see the voltage and frequency control, then we will see the power control. So if the coupling converter is a voltage source converter, so a current control strategy can be used to determine the reference voltage waveform for the pulse width modulation. Yes. So the reference I will show how the voltage and frequency control. This is the grid following power export control, the voltage control. So first is the grid following power export control. So the first way is the reference signals are synchronized to the microgrid frequency by tracking the DC voltage waveform. The control strategies can be implemented in a synchronized DQ frame. That is, we are converting ABC into DQ, and then from DQ components of the converter, output currents corresponding to the real and reactive power. That is ID. We will take ID and IQ, and from D-axis and Q-axis current components of the VSCs are excited through and ABC to DQ, that is ID not ID and IQ. So then they are compared with the reference signals, D reference control ID and as well as Q reference control IQ. That is ID out from ABC to DQ. We will compare with this reference control ID reference. Similarly, IQ reference is compared with the IQ. So the error signal are applied to the DQ current control lag to determine the D and Q components of the voltage, reference voltage signals. That is VD and VQ. Finally, through again this VD and VQ, we are converting into ABC by using this DQ conversion. So from this, we will achieve VA, VB, and VC, three-phase reference signals for the PW signal generator, and from this PW signal, it will give the firing angles to the converter such that a particular power flow control will take. So details of the internal and external control blocks can vary based on the control modes and the type of memory source. So similar current control approaches can also be developed. Similarly, we can obtain current control approach also. Here, this is voltage control approach, and then we obtain current control approach also with the same example. And if you want power export, this is a grid following power export control. This is if you want a power export controller strategy in which the DC link voltage controllers and the reactive power control replace the here. See the DC link reactive control and replace the reactive power control. That is here DC link we replace with the reactive controllers and again similarly see here our voltage VD reference is compared with the VDC and the error signal is given to VD's control and it will produce ID references. And again this Q1 to Q reference control compares with this and error will be given to Q control and it will produce IQ reference. And it is compared with the ID and then we will get this closed loop and finally we will get the DQ to ABC output voltage and from that we can obtain the power export control. So this is the typical grid following power export control diagram. So next we will see the power dispatch and real and reactive power control. How the power dispatch real and reactive power control. This is a diagram. In this power dispatch and real and reactive power control strategies are normally used for output control. Normally for output power control of dispatchable DRMs or power control of dispatchable DRMs using pre-specified reference values for real. So that is a P with specified reference value real power, and as well as reactive power compensation. So this figure 6 shows the active and reactive power control block diagram. In this, see the P reference and Q reference are the power set points, and P out and Q out are the real and reactive power outputs calculated from the measured output voltage and current of the particular unit. So the P reference and Q reference values can be set by a supervisory power management unit or locally calculated according to the pre-specified power profile, or to optimize the real reactive power export from the unit. Already the reactive power export from the unit. Otherwise, from optimization method technology we used, and we have to calculate the every time we have to measure the voltage and current, and finally we can calculate the P out and Q out. And these two are compared with this, and we will give the PI control here. Again, this limiter is there, the output is ID reference. From this, we can achieve the active power control. And from this, if you want reactive power control, so this Q reference and Q out is compared, and the arrow signal is given to this reactive power controller. See here, this will go the IQ reference, and from this IQ reference, we'll again convert into DQ into DQ current control. What we have seen here, current control. Current control here again we are converting into VDDQ, and from this we will generate the PWM signal. From that we will control the active and reactive. So this is about the two controllers from the power flow controller. That is you will get the voltage and as well as frequency control and the active and reactive power. So these are the active and reactive power control, and this is voltage and voltage control. Otherwise, we can go for the current control also if we replace this one. So this is the diagram grid flow good following power export control of voltage control and as well as current control. And this diagram will show you the active and reactive power control, how to control the active and reactive power. So this is about the two types of controllers. And next we will go for the microgrid supervisory control. So the main objective is achieved through either centralized or decentralized supervisory control. That includes three hierarchical levels as shown in here. See, there are three hierarchical levels. So distributed net here the DNO is called a distributed network operator, and MO is market operator. Actually, these two will not in the supervisory control. So only this is, for example, if number of microgrids are there, so we have to see the microgrid controller. So this here from this the supervisory control stops. That means DNO and MO are not within the system; they are outsiders. They are not in the supervisory control; they are outsiders. So microgrid central controller. So this plays very vital role, and LC is a local controller. So that means what I mean to say is DNO and MO comes into the picture if number of microgrids are formed together and they formed a big microgrid, then only their DNO and MO comes into the supervisory control. Otherwise, if only one microgrid is there at the time, and DNO and MO are not inside, they are foreigners, they are outside of the controller. So that means what I mean to say is the DNO, distributed network operator, is intended for an area in which more than one microgrid exists. That means it is comes into the picture when more than 2 or 3 microgrids are there. That is, in addition, one more, that is market operator is responsible for the market functions of each specific area. So these two already I mentioned. These two entities do not belong to the microgrid. They are not belongs to microgrid. They are just delegates of the main grid. They are delegates. They are not comes into the picture of supervisory control. Next, the main interface between the DNO and MO and the microgrid is the MCC. So see, the MCC interface the DNO, MO, and microgrid, that is local grid and with local grid. So the MCC assumes different roles. It plays different. It acts as in different ways that it performs the different tasks, we can say, ranging from the maximization of the microgrid value to the coordination of the LC. So maximization of the microgrid value and to coordinate the all local controls. So MCC have different tasks. It performs different tasks. In that, one of the main is it maximizes the microgrid value and coordinates the LCs. So then, what is LCs? Local controllers. LCs controls the distributed energy resources units, and the controllable loads. They will control the distributed energy resources and controllable loads within a microgrid. So within a microgrid, LCs controls the distributed energy resource and as well as controllable loads. So depending on the control approach, that is depending on the control approach. So each LC, each LC may have its own intelligence. They have their own intelligence. For example, if the microgrid is set to be in a central microgrid, already we have seen two controls. There is central control and decentralized control or distributed control. So in centralized control, if this microgrid set, what I mean to say is, I'm repeating again. So DMO and MO, distributed network operator and market operators are the just delegates. They are not at all comes into the inside of the supervised control. So if more than 2 or 3 microgrids are there, number of microgrids are there, then only they will comes into the picture. And this DMO and MO are interfaced with the microgrid through MCC and microgrid central control. So the microgrid central controller, there is a microgrid central controller plays different performs different actions. So that in that main action is it has to maximize the microgrid and as well as it takes care about the local controllers. And again, so the local controllers are obtain the signals or obtain the control signal from the MCC, or otherwise MCC control this LC if the microgrid is centralized control. Even though the LC has its own intelligence, each LC has its own intelligence, and every time the LC purpose is to control the integration between the DER and as well as control loads. And if the microgrid is in centralized controlling mode, then LCs, they are not using their own intelligence. They will simply follow the signals or control signals given by MCC. That is, please concentrate here. If the microgrid is in centralized mode, at the time that even though the LCs has its own intelligence, but they will not use their own intelligence. They will simply follow the signals given by the MCC. In centralized operation, that is, in centralized operation, each LC receives set points or control signal from the corresponding MCC. Whereas if decentralized operation, at the decentralized operation, LC makes its own decision locally. That is, they will take their own decision, and LC does not require a command from the MCC. At the time, LC have no control, or that is, LC has no control. LC is not controlled by MCC. That is, MCC is not at all controlled by LC. LC use their own intelligence and they will take the decision locally. In that case, the LCs will not take care of the revenue and all those things. They have to take care of the contributed supply. That's it. They will not take care of the revenue and all these things. That is in decentralized operation. This is very, very important. What happens when LCs in centralized operation? At the centralized operation, LCs follow simply, even though they have intelligence, they will not take the decision. They will challenging one. So it requires every time it has to process the data, and the used data has to be processed. And here there is a lot of challenges. In decentralized mode, LCs they will take a decision their own self by using their own intelligence, and at that time they will don't bother about the revenue. They will bother about this contributed supply. So next we will see centralized and decentralized microcontroller in very in depth. So centralized microcontroller. So this is C. So a centralized controller, the MCC, already I mentioned, the MCC optimizes the microgrid exchange power with the host system, that is maximizing the local production depending on the market price and security constraints. So here MCC takes care of the maximization of revenue and as well as production, and it will take care of the market and security constraints. So this is achieved by issuing control set points to DER units and controllable loads within the micro. So these all these are dependent on the micro. That means here the MCC they require a high-end processing system that has every time it has to take the data, and from that it will process the data and it will compare the market price signals and as well as what is the it also requires the data of DER, and from the data of C here C stay like. So here the information is exchanging centralized controllers. So see this every time it's giving the signal to the LC. So by taking care of bits of DER and as well as demand side PD, it processes the data and every time it is giving the signal to the LC such that which DER distributed energy resources is to the higher that is takes more active, and which DC DER unit is to be shut down or which DER is to be overloaded or highly loaded or maximum loaded. That is depending on this one. That is the communication can through telephone. Here the communication can through telephone lines or power lines carrier or wireless media. So the MCC takes a decision for pre-specified time intervals. That is example every 15 minutes for the next hour or hour base. That is depending on the program set here. Based on the market prices and unit capacities, the DER LCs issue bits, the DER and LCs issue bits to the MCC regarding their production levels. Similarly, the load LCs, that is load LCs, issues bid for their demand considering their properties for service. So based on the market policy, the MCC takes into account DER load bits. First, you process the DER load bits, or otherwise market price, network security constraints. It also take care of the demand and or renewable production forecast, and using an automation process issue. That means it will take the forecasting data, previous data, and future data, and it will process by using its own automation process and issue the signal depending on that one. And production set points for DER. This diagram gives the production set points for DER units, set points for the loads to be served or shed. That means which load has to be shed and which load has to be served. Already we mentioned in the starting itself, the MCC always takes the care of the balance between the DG and as well as that is power generated at the DG units and as well as loads. So and it also take care of the market price for the next optimization period to enable LC bidding process. See this diagram. Clearly gives the microgrid central controller what it is using. Here, a lot of communications technology are implemented. From the lot of technical implement here, the to it every time it will take the data from this, all this, and it will also take care of all the market prices and network security constraints, and then it takes the data and it covers the data and it processes the data here. And this by processing data, it will use the automation techniques, and from that it will take the decision which DER has to be loaded up to its maximum, which DER has to be loaded and normal loaded, and which DER has to be removed. That is depending on this the microgrid central control works. And next one is that is what I meant to say, based on the MCC microcontroller control issued signals, the LCs, the local controls, adjust generation and demand levels and prepare bits for the subsequent periods. So the functions that can be implemented to perform centralized control of a microgrid includes load generation, load or otherwise generation heat forecasting and functions regarding unit commitment, economic dispatch and security constraints. So here we will show the one, we have taken one example of this centralized controller, MCC controller, how it is controlled. See this for a 24 hours here, for a 24 hours we are showing here. So this is you see this is orange. This orange is orange portion we are giving. The load is supplied from the grid, that is utility grid. And if you see the green one and as well as yellow, we are obtained from the micro turbine and as well as fuel cell and as well as wind. And from this, that means from morning from 1 to 8, there is no renewable energy sources. At the time, micro MCC issues the LCs to take the power from the utility grid, and from 8 to 18 hours, from our 8 to 18 hours. So the microgrid central controller process the data and it founds that it is feasible that that is microgrid, that is renewable sources are lower cost, then it will penetrate the renewable sources in the load cycle, and then it will take the power from the here, and remaining amount of load is supplied from the this grid. And from 18 to 20 again, the total microgrid is not at all comes into the picture. The MCC issues a signal that total load is supplied by this 2D grid, and again see the from 20 to 23. So again microgrid comes into the picture, and from 23 to 24 again total utility grid is supplied. So this is the centralized controller data. We have an example of daily activity schedule of 24 hours is taken for your reference. This is about the centralized control. Then we will see the decentralized microgrid. The decentralized control approach intended to provide the maximum autonomy for the DER units and loads within a microgrid. So the autonomy of the LCs implies that they are intelligent and can communicate with each other to form a larger intelligent unit. Already I mentioned in decentralized controller, the LCs use their own intelligence and they will communicate each other and they form a larger intelligent unit. In decentralized control, the main task of each controller is not necessarily to maximize the revenue. Already I mentioned their aim is not to maximize the revenue. Their aim is to provide the continuity of supply. Right? In decentralized microcontroller, the LCs issue its own signals and they don't bother about the revenue. They will bother about the continuous supply. So thus the architecture must be able to include economic functions, environment factors, and technical requirements. So these are the duty functions we have to incorporate it along with the decentralized microgrid, that is controller. So this is the main feature of the MAS here. Multi-agent system is to incorporate what are the demerits in the decentralized. We have to incorporate all these things. So this is a block diagram of decentralized microgrid control structure, how it's utilized, and what are their this controllers. And another thing is here see the DNO and MO, and here this is up to this is only our centralized controller, and in the decentralized controllers, LCs takes place into the picture, and LCs will take care of all the signals there to the, that is, they will issue the signal to the DG unit such that their main motor is to supply the continuous supply. They don't bother about the revenues. So then we have seen the centralized control and decentralized control. So now we'll go for the comparison between centralized and decentralized control. So here, see, if you see this diagram, so control hierarchy, there this one is centralized and this one is distributed or decentralized. So here, see the computational cost and complexity. Obviously, centralized controller has high computational cost and as well as more complexity, because already I mentioned in the centralized controller, the MCC has to collect the data and it has to collect the huge amount of data and it has to process the data and and it has to choose the accurate optimization techniques, and from the optimization technique it has to find its own solution and that is right solution, and then only issue the signal. Whereas in decentralized controller and distributed controller, there is no computational cost. That LCs takes their own decision by the use of their own intelligence, and from that they will control the failure. Then communication facilities cost. Obviously, centralized control requires most communication facilities. That nowadays all these SCADAs are replaced with the PMUs, weather measurement units. That means each weather measurement unit cost is around 50 lakhs. If you want to build a own also, you will take 3 lakhs to 4 lakhs. That means communication facilities are required for here, and the cost is more in centralized. And decentralized, no need. Also, LCs, there is no communication because between the MCC and LC. Between the LCs, there may be a chance of communication, but it is not at all. It is not. If it is not occurred also, it is possible decentralized control. That means so the LCs can work. Next, flexibility and expandability. Obviously, centralized has no flexibility and no expansibility because it is already developed what you will develop. But in decentralized, we can switch from decentralized to centralized by adding all these communication facilities on this. That means expandability is possible. And reliability again, decentralized low reliability because a huge amount of data has to be processed and a lot of complicated complexity is present in this, so that's why reliability is low and distributed reliability is more. But implementation difficulty low and this is high. This is a brief comparison between the centralized and distributed control hierarchy. Next, energy management system. Next one is energy management system. The intermittent sources. Already we know that the intermittent sources, that is the renewable sources, are not trustworthy. So we cannot trust on this intermittent sources like renewable sources, wind, solar, all these things. That's why definitely we required energy management system. So that means an energy storage system we required. So EMS here the energy management system ensures the system in a reliable, flexible, and quality manner such that the available distributed generators are utilized in an optimized manner. So basically, in rural microgrids, the intermittent sources are incorporated to local microgrids like RES, wind, solar, along with the diesel generation are associated to back up the system as well as to meet the electrical load demand. So what I mean to say is energy management system is definitely required. That is, the energy storage system is definitely required. So we'll see first what is the prime. I will explain later this one, this item. Otherwise, I will explain here. So here, energy management system, energy storage system, definitely these are energy storage system. This is energy management system, smart energy management system. So it has to be take the data from this, and every time it has to be take the data of ESS and as well as forecast data of DCS and load also. It has to be take the data from the load and grid, and it has to be analyze the data in its optimization mode module. And here we have to choose, we have to form the optimization problem, and for particular problem we have to choose our sophisticated optimization technique, and then we have to take the decision such that it has to issue the signal such that issue the signal to the grid such that the grid has to be serve the load with the renewable energy source or with the utility or from the ESS. That is decided by the automation module. So this is the smart energy management system. Before going to this, we will see what is the energy management system prime duty. So the prime duty of EMS is to create a balance between supply and demand in an efficient manner. It should be cost effective within operating constraints and uncertainties in the EMS architecture. Then it can work for real-time SCADA applications, dispatch control, energy scheduling, and accounting as well as transmission security management. Then the energy management system is becoming more and more complicated as the grid is evolving with the integration of PES and RES and resource storage systems, buildings, high power equipment, and many more factors. So, but in energy management system, Internet of Things and machine learning play and artificial intelligence plays very vital role nowadays. A lot of research work is going on in this. recently I have given one lecture on this one. That artificial role of artificial intelligence and machine learning on energy management system, that is energy storage system. So nowadays that is also a hot research area. Just now the researchers are attracted towards that area. So that is a new area. So if any faculty members or any researchers they want to form an objective there, that is a use of artificial intelligence, that is use of artificial intelligence and as well as machine learning towards energy storage system, that is EMS. In EMS we require artificial intelligence and machine learning and we require automation techniques. So this is one of the area we can the researchers can do much more. They can publish much more papers. So recently I have taken this topic in one of the college. So that is artificial role of artificial intelligence, there is machine learning in energy management system or energy storage system. So okay, ready. So this is the researchers who wants to do research. So this is one of the area you can go ahead. So because slowly the people are attracting this. This is a new topic to the most of the researchers. Only less number of researchers they are doing this research in this area. That means there is a lot of scope to the researchers to do something in this area. Next one is functions of EMS. What are the functions? I'm not going in depth because Professor Arvind Singh has taken this topic in BSSUT last his previous lecture. I have gone through this one. So some of the points I took from his yesterday lecture. I have taken this. So simply I will read it and I think you gone through it. Those who are not present yesterday, just I'm giving the points. Functions of EMS, there gives a clear picture about the energy cost involved into production of office. It helps to optimize and monitor electrical parameters to achieve cost reduction and helps future planning based on consumption pattern from the EMS system. So the future planning just definitely require artificial intelligence and machine learning in the EMS system. So this is one of the objective for the researchers. Then measuring your energy consumption and collecting the data. So collecting the data is required. Without collecting the data, you cannot go for the smart energy management system. So every time we have to collect the data, we have to process the data, and according to the knowledge of your previous history and forecasting data, you can choose your own optimization technique. Then only you can issue the control scheme. Then finding and quantifying opportunities to save energy, as targeting the opportunities to save energy, so tracking your progress at saving energy, significant savings, and open opportunities for energy innovation. So these are the functions of EMS. Some of the functions of EMS. So I have taken this some of the points from yesterday's lecture. So from Professor Arvind Singh from Arvind Singh from China, Shandong University, China. So next one is the advantage of EMS. So what are the advantages of energy management system? Cost-effective solution. So no human errors in data collection. That means because we are using sophisticated data collection points by the use of PMUs. Nowadays, all the PMUs we are using their process the data. So that is collecting the data and without any delay, we are time stamping data. We are transferring to the central controller with the help of satellites or optical fiber. So then easy to configure and maintain. So configuration easy and maintenance once you include all these things, configuration and maintenance easy, and helps to identify inefficient electrical equipment. Obviously, which one is not using and which is not feasible, then we can remove that with the help of all this process data. Then maximum power time analysis. That's the facility of viewing real-time electrical data and energy reports or internet. Then graphical display of energy consumption and alerts. Alerts also we can obtain. This is about the function of EMS. Then the objectives of EMS. What are the objectives? So an EMS may have a single objective or multiple objectives that may be technical, economic, techno-economic, environmental, and social economic. So these are the objectives of EMS. Then the EMF is becoming more and more complicated as the grid is evolving with the integration of EVs and RES. I know I already mentioned that nowadays all these renewable energy sources are penetrating into the normal grid. That is with the help of PMUs and all this. That means Indian government wants to make our conventional grid into smart grid with the by incorporating or integrating all these PMUs. They are replacing all SCADA with PMU, and as well as they are using sophisticated technologies, and they want to omit all these conventional sources with this renewable sources. So if these renewable sources comes into the picture, so definitely there is a lot of challenges and lot of problems we have to address. So for that problem, one of the solution is EMS is becoming more and more complicated if RES and ESS are penetrating into the system. Next, integration of PEVs and ESS and the RES without proper coordination may cause the system to deviate from the intended performance. Yes, obviously. If the integration of PEVs, ES and RES are not improper, so then obviously our main objective will not be achieved. So then technical abilities of EMS include power quality, equipment performance, and the degradation of transformers, and its consideration provides better performance of the system. So better power quality, improve life expectancy, and reduce maintenance and downtime. So technical objectives of EMS, these are the it has to achieve power quality and equipment performance like that. So next, economic objectives also has to be achieved EMS. That is what I meant to say is the energy management system has to generates the signal such that it has to take the decision which whether we have to go for the utility grid or either we have to go for the microgrid or we have to go for the energy storage system to achieve the revenues. So then environmental objectives, it has to cover environment, it has to fulfill environmental objectives. That means emission, it reduces the emission of greenhouse gases, where different fossil fuel gas generating power plant has to be removed, and we have to schedule RES and we have to use RES with the help of EMS. Next, social economic based objectives has to be achieved, and the benefits obtained from social welfare based program is shared among all the players, including the end users. So these are the objectives of EMS. I'm not going in depth because already I mentioned Professor Ram Narayan Singh has taken yesterday, which he explained very well. So next one is the typical energy storage configuration, how it looks like. So I want to show this one. The typical energy storage configuration in EMS or for power grid, microgrid. A typical energy storage configuration comprising of energy source. This energy source either fuel cell or this wind turbine, or otherwise this is a solar. Here is solar. So fuel cell, wind turbine, and including the energy source are the AC load interface as well as the main power conversion system. So the control here, this is the source interface and PCS. PCS is the power conversion system. Definitely these are converters on the control device, and finally the energy storage media, the energy storage system, and the demand side. This is the demand side. So the electricity generated either DC or AC passes through the necessary conversion passes through necessary conversion stages. That is the use of PCS in. There is a source interface in order to be stored mechanically, chemically, or in an appropriate form of electricity. That is decided by this one. If it is electrically, it is stored in the batteries, and if it is mechanically, it is stored in the turbines like this one. And if that means chemically or electrically decided by the species. That means what I mean to say is if the energy is surplus, then the electrical energy is converted to chemical energy and it is stored in the battery. If the supply is not suitable for the, that is, it is not sufficient for the loads, at the time what will happen? ESN has to be control send the signal such that the energy can be, that is, the chemical energy is not into electrical energy, and this is given to the load. This is whenever an energy deficit, that means just now we discussed, whenever an energy deficit appears on the demand side, so energy deficit appears on the demand side, the required amount of energy is drawn from the ESS in order to eventually convert. That is here we are converting DC into AC, and AC is going to the load. So note that we have to take care of the note. We have to mention. Remember that the source and the AC interfaces, along with the control device and other auxiliary systems, are better known as balance of the system. That is called as BOS. Here, what I mean to say is in the energy management system here, the energy source is it may be a wind, or it may be fuel, or it may be conventional with the help of source interface, and the controller panel decide issue the signal if the load is load is met and the energy is surplus, then it issue the controller to the PCS such that it has to give the energy, that is, it has to store the energy in the ESS. And if the demand is load demand is not supplied with this energy, so at the time the control panel issue a signal to the ESS such that the stored energy, that is chemical energy, is converted into electrical energy and it is given to the load. That is, load can be supplied from this. So, and we will see the main components of typical ESS system. So already we have seen energy storage system. So energy system may be battery, that is electrochemical or electromechanical, or electrical. So then that is electrical means supercapacitors we can use. Electrochemical means batteries. So then interface of AC load and source, already we mentioned that protection device, voltage transformers or converters. Then power conversion system, that is rectifier, DC switching and protection device, auxiliary systems and accessories, electrical parts, interconnecting, protection devices, charges, mechanical parts, there is diagram support, water, heating, air and fluid pumping system, safety equipment, refrigeration system, vacuum. Monitors and controllers, see here we replace monitors and controllers. So monitors, there is the diagnostics, there is storage media, power consumption, subsystems. And the controls will be storage media, protection devices, power conversion subsystems. And facilities are foundational structure, lighting, grounding cable, heating, ventilation, and these are the components of a typical energy storage system. So this one is the components. So next one is the energy management system, the future energy management system like this. This is the future energy management system. So here see it has to take the every time it has to check the power from the sources, renewable sources, and it will, if the supply is more than the load, then it has to store that energy in electrolyzer or if in a fuel cell. Sorry, in the fuel cell, not fuel cell, electrolyzer and in battery. So there are two. What we have see here, electrochemical and electrical. So that is electrochemical is battery, electrical is electrolyzer. So then if the load is more than this generation at the time, see this can be, this battery is recharges and it will supply to the load. And additionally fuel cell also there, and here the battery electric vehicle charging station is there. And if the load value is more than this renewable source and as well as stored energy, then we will go for the utility. This is the energy management of a microgrid coupled to a V2G system. Coupled to a V2G system. The energy management of a microgrid coupled to a V2G system. So this is a typical energy management system. How the energy management system works. What we have seen in this. What we have seen in this. Same we have seen in here also. This is similar smart energy management system. So this energy management system with energy storage configuration, same we have seen, and the same we have seen in the table. The single line diagram which gives the energy management system. So of a microgrid coupled to a V2G, so that is coupled to the grid connected microgrid. In this, if you see the power generation of renewable energy sources is less than the load at the time. So the battery energy can be drawn, and as well as fuel cell energy can be drawn, and as well as the grid also will supply the loads. For example, if the renewable energy sources gives more energy at the time, so the load served from the renewable energy source, and as well as the surplus energy is stored in the batteries, and as well as electrolyzers. And this is the single and diagram of energy management of an microgrid coupled to a V2G system. Next, we will see the demand side management. So, demand side management has gained more attention in the electric power market domain. So, in order to obtain economic benefits for utilities as well as consumers. So, this is the classification of demand side management. How it is? So, demand side management. There are two categories. There is customer induced and utility induced. So then again, the customer induced can be classified into two categories: demand response program and energy conversion. Again, the utility induced can be classified into Q1: strategic load growth and flexible load sharing. So out of this again, this demand response is classified into two: intensive based and price based. Again, intensive based is classified into load management and market based. Again, price based is classified into time of use, real time price, and critical peak pricing. So demand side management is very vital role in the agri power market. So this is a big classification of DSM in this, and this demand response is a strategy to monitor load variations such that the grid can operate sustainably, along with the additional features to provide impressive benefits such as price reduction and reliability of the system at the convenience side. So demand response is a it always monitors the load variations, and it can have additional feature to that is it gives every time it processes the data, and from the data we have to go for the reduction the reliability of the system to consumer end side. So here the figure shows the demand response architecture of DMS level. See the network model, regulator market, operating model. Every time it has data from the metadata management, it will cut the data from the metadata and it is given to metadata. See, the DR engine receives the metadata from the metadata management system, which receives and collects the data from the individual customers. So every time all individual customers has to data is collected in the metadata management system. And this metadata management system, it is given to DR2 interface, and this DR will take care of the load forecasting and demand response, and it processes the data, and from the data it issues the signal. So this is about the demand response. I'm not going demand response in much more depth. It's just I'm giving this diagram demand response. Then so that is about the microgrid management and controller advances and controllers, and then we will see for the type of optimization problems. So I mentioned at the starting itself, I have gone. If you see in my lecture, or if you see in our discussions, I mentioned the objectives in wherever I found the objectives I have mentioned, because forming the objectives is very difficult for researcher. So once you form the objective, it is easy to achieve. So for to form the objective, most of the researchers they took 6 to 7 months, or sometimes they will took for 1 year to form the objective. So in this lecture, I am trying to give at least I am very happy. Otherwise, my lecture is fruitful if I will inject, or I will induce, or I will infuse at least 2 or 3 objectives. But if you see in my lecture, I have given around 4 or 5 objectives, which are trusty areas nowadays. So then this is my two of my students are working in this optimization problem. So they are academic research and optimization. So I'm not giving the derivations of what is optimization, all this thing. I'm not doing. Just I will give the idea, and here a proper automation algorithm needs to be selected according to the type of the problem. Basically, first you form the problem, then according to the problem we have to choose the proper optimization algorithm. So generally the optimization problem can be categorized according to the nature of the objective, constraint functions, that is they are nonlinear or non-convex, or smoothness of them is non-differentiable. So although it is difficult to provide a detailed classification of optimization because of large number of subfields and multiple links, generalized taxonomy is given by NEUS. This is a network enabled optimization system. The references are given at the end of this one. In this figure, if you see the which you see this is the optimization taxonomy from the optimization textbook. I have given the reference down end of this session, this, presentation. So optimization, it can be divided into three categories, that is uncertainty, deterministic, multi-object optimization. So here I want to mention here multi-objective optimization. Objective optimization is a very hot research area nowadays. Most of the research is because this optimization technique is almost get saturated in the very single objective optimization. Now the researchers are very much eager and very much interested to do the multi-objective optimization. So multi-objective, multi-optimization techniques they are using, and they are achieving the output. So anybody, those who are interested, those who are doing, or those who are interested to intended to do the research work, the multi-objective optimization is a very trusty area. So you can go, and that is easy to publish the papers, because if any field, if you are new and new player, nobody is there in the ground, so you can nobody is there in your ground. Sorry, nobody is there in the ground. You are the one. You are the player. You can do anything. So once more number of the people came into the ground, so most of the competitors are there. Okay, madam, is it my voice is audible? Hello, hello. Yeah, yeah. Almost I am at the end of within 2 minutes I will finish. Yeah, yeah, yeah. So that means here this is the types of automation problems. So this is a I'm not going much more in detail because time is less. So automation technology taxonomy, this is and I want to give the objective function here. Multi-objective optimization is plays very vital role nowadays. So this is what we can do in this. Next one is I'm just being the domestic optimization versus stochastic optimization. Uh, and this is continuous optimization versus discrete optimization. So I'm not going that in that much. Next section will be about that I want to finish. So then next one is constraint optimization versus unconstrained optimization. Then this table is very important. My student, this table, the references are there, and this table is very important for the researchers who want to do their research in automation techniques. So we found the foundational type, approach, and objectives. My two students took around 6 months of they dedicated that 6 months time to make this conclusion table. So that means they made survey, and they did review, and they published the paper. So if you want this table references, I will give the published papers DOS, and then you go to it, and you will get the details. This is the survey of optimal scheduling objectives considering the formulation type and adaptive approaches. What are the approaches taken by the different published papers, different researchers, different scientists they use, and then this is a continuation table. So this is a continuation of the table, and then that is a optimization techniques. So next future directions in this as well. So all the numerous efforts have been made to enhance the planning, operation, control of entities. There is still room for innovation and improvements to develop and apply various models to our campus. Already I mentioned the microgrid has opens to different branch people, computer science, EC, and as well as electrical. So and there is a centralized and decentralized. To obtain the compromise solution from the centralized and decentralized, we required a lot of work we have to do. The centralized, a lot of data has to be processed. That means most of our automation algorithms we can go in centralized automation. There is a chance for the researchers to do something in this area. And then one is risk limiting dispatch, and there is virtual, and another one is virtual power plants. Nowadays, most of this work is going on virtual power plants. So this term is new for the most of the research work people. So virtual power plants nowadays still they are in the literature, still they are not at all existing, but virtual power plants plays very important role in future. So this is the future microgrid. How the future microgrid looks like. So already I mentioned. So in future, number of small microgrids they form together to make form a big microgrid. This micro microgrid serves the purpose of the loads of that is municipal loads, not in the area of 1 kilometer, 2 kilometers. The researchers aim to serve the loads in a 10 kilometers area. That is, we have to supply the power to the loads, municipal loads. So there's a lot of research work is going on, and these are the references for this PPT. And the red color is the references. Those who are very much interested to do the optimization techniques in academic dispatch. These are the papers. This one already came online. This is yesterday only it came online, second paper. So you go through it, and in this you will get all the details of the automation techniques which were used for which uh, purpose. So thank you, and any queries? Thank you, madam. Hello. After that, no, not now. After that, also you can send the queries to madam, and she will convey that through this one through email, or then I will answer it. No problem. So my aim is to just my aim is to just ignore at least one or two people are benefited from this my lecture. That's fruitful for me. If anybody is inspired, thank you very much. Once again I would like to thank Papier and Madam for giving this wonderful opportunity to my research work. Thank you very much, Madam. So, shall I leave it?
Hello, Dr. Bhavya, can you hear me?
Yes, answered.
Okay. I am here, and expert Dr. Naveen Marathi is also here. Huh? Okay, we are already here, so just give.
Also, please, so,
Okay, okay, madam. Thank you. So, Dr. Naveen, should we start, or we can wait for just couple of minutes?
Yes, sir, no issues.
Yeah, because people are actually engaged for
Yes,
2 hours. So
yeah, listening in online it's very difficult. We'll
Right.
give a break for 5 to 10 minutes. I don't have any problem, sir.
Okay. I'm here only, so we'll
Yeah, no
just
issues.
take a couple of minutes. We will start. We will start. Actually, now my clock is 16:25.
Okay, sir.
So exactly after 4 minutes, I will we will
Sure.
start the session with your introduction.
Okay, sir. Thank you.
Thank you. So I welcome you all in the uh, last session of uh, today's lecture series. Shall we start? Dr. Vishal, Dr. Biswal, Saroj Panda, Sarkar, Vibhuti
Yes, sir.
Kavta.
Yes, sir.
Yes. We are waiting. We are waiting.
Do you want more to wait or we shall start?
Start, sir. We'll start, sir. Now. No problem, sir. We'll start now.
Okay, let me do it. Okay, thank you. So it's my pleasure to introduce our next session expert, Dr. Naveen Kumar Marathi, who is presently working as a senior engineer, Powertronics division of Velo India Private Limited. So I pronounce you, maybe most among of you may not familiar with the R&D center's profile. That is Velo, VALEO. So you can Google. So it's a French-based R&D center specialized in the area of autonomous and electric vehicle. Uh, if I am doing some mistakes, so Dr. Naveen can later on correct me. So it's a headquarter right now in India is the Chennai. That is the full-fledged R&D center in India. And you can appreciate that Dr. Naveen is dealing with the power electronics division. The head as a power electronics I'm sorry all. There was a bit interruption. I hope that you can hear me. So it's a pleasure of being in government institutes. So okay. So let me continue. So Dr. Naveen Kumar Marathi is right now is associated with the head senior engineer Power Electronics division of the Velo India Private Limited R&D Center. Earlier, he before joining the industry, uh, he was with the Srinagar University, Greater Noida, as a research scholar from 2013 to 2017 with the Department of Electrical Engineering. He obtained his master's degree in the area of computer engineering from Rajiv Gandhi University of Knowledge Technology, that is the Triple IT Andhra Pradesh, in 2013. Prior to that, Dr. Marathi obtained Bachelor's of Technology degree in Electrical and Electronics Engineering from CRB College of Engineering, JNTU, Hyderabad in 2009. He has published 12 papers in reputed journals in IEEE conferences, including IEEE Transactions in Power Electronics. He also authored one book chapter in the Springer. He received couple of best paper and best project awards in various IEEE conferences and in IEEE Congress. He also was among the top finalists as far as the TI innovation contest, and um, also received some cash prize and the merit list. He is an active reviewer for IEEE transactions on power electronics, IEEE transactions on industrial electronics, energy conversion, and in many other reputed journal and conferences. Currently, he is a publication chair and the steering committee member of IEEE conference SCFET 2021, uh, where the window has been is opened yet, and you have an opportunity to participate in that particular conference as well. He is an active volunteer of IEEE Hyderabad section. He has delivered more than 20 keynote on the or guest speakers in the various FDPs in the topic like IoT automotives, electric vehicles, hybrid electric vehicles, global scenario of automotive in electrification. His interest, current research interest includes power electronics, digital control of power electronics, electrification in automotives, HEV, electric vehicles, IoT in automotives, charging station, etc. I welcome you, Dr. Naveen Kumar Murati, for this particular session. His topic of lecture in the present session is IoT in automotive electrifications. So with this, I'm handing over to Dr. Marathi to listen for the couple of hours. Thank you.
Thanks a lot, sir. Thanks for inviting me and a nice introduction. So it's my pleasure to be part of this Tech FDP or a professional development course. So with this, I'll start my presentation talk. So hope everybody could see my screen. So today's topic, as it was already given, Internet of Things and its application of automotive, or its application in automotive electrification, or different varieties of research areas of automotive. So most of the topic I'll be dealing with what presently we are doing in the industry, and what exactly we are looking from academic perspective, what kind of research we are doing, and what kind of collaborative projects have been involved in the academia as well as in the research industry. So so if you think from an academia perspective, this may not be like a complete in-depth talk. I will be going on a single topic, but I'll be talking on various applications of automotive areas where we are doing exactly Internet of Things, and what kind of approach we are following to arrive at the particular solutions. So in my figure itself, you can see in the right side how what kind of transportation segment or the automotive division. So both the things I'll be touching upon with the IoT technology. So as Dr. Gyanranjan Biswal sir has introduced, I am belongs to the Value, which is an R&D center located in Chennai in India. So as far as Value is concerned, we are presently at the 33 countries across the globe, and our presence, our footprint is there in almost all the continents. And we are currently with 133,000 plus employees on roll with Value, and there are some off-roll employees. And at Chennai, we has a global technology center, we call it as. We have all the divisions, including the powertrain systems, comfort driving assistance, thermal systems, and as well as the mechanical and software systems. So these all groups, we work in together to deliver a project to the customers. And we are the tier 1 suppliers for almost all the global top range OEMs. And we are mainly into the European market, and now our footprints are also established in India, and we have started with some of the major OEMs like Mahindra and Toyota, Maruti, and all these OEMs are part of our customer list. So with this, I'll move on to the today's talk. So this is my agenda for today, and there's an introduction, and basically I'll be talking about half the at least 30 to 40 minutes of my talk will be on why and how we are framing the IoT or any problem when we are talking about in IoT. So this is a buzzword across the any place when you talk now. The buzzwords are IoT, deep learning, and machine learning, AI. But why exactly we are going for IoT? What is the necessity in IoT, and what are the market drivers to look for the IoT, and how we have to framework? If any problem we are thinking of, how we should framework the problem, and if you have to framework the problem, what are the steps you have to take into the considerations, and different application areas where IoT is making its footprints, and how it is establishing its customer relations, or from if you talk about a simple manufacturing process, the industrial 4.0 revolution is going to be top notch with the IoT technology, and a reduction of many things or the advantages we will be seeing. Then straight away we'll be going to IoT in automotive. Then I'll be talking about some of the real-time examples, what products we have made with the IoT, and what kind of autonomous systems we have developed, and what kind of applications in real time, real environment we have tested on the roads with the vehicles. So this I'll be presenting to you all. Then some touch I'll give on IoT in transportation segment, and the challenges and opportunities. Most of the time I'll be talking all the challenges and opportunities through my slides only, not in the specific way, but I'll be giving some of the examples where I have been involved in some of the projects and the future roadmap, and then I'll be concluding with this for the session. So straight away, if we talk about IoT, before 2009, there is no word called IoT. So, and before 1995 or 94, we don't know about internet. There is only the communication between some protocol based TCP/IP or the ARPANET, where the area of research network, where they used to connect between the machine, and in the same laboratory they used to send or receive the communications through some chat box. But now in this modern era of 2020, what you could see what happens in internet in 60 seconds. So this is from a research organization. I got this picture. You could see in a 60 seconds of in internet, there is a mass involvement of people is done in different aspects. If you see in a single minute, you can say 375,000 apps are downloaded in 60 seconds, and 2.4 million snaps are created through internet, and 266,000 of hours are watched in the Netflix, and 1.1 millions of swipes are done in the Tinder, and 973,000 logins were done, and 3.7 million searches of queries have been done in Google. So you can imagine how the people are addicted to the internet and the technology, you can say. So overall, now everybody from a small child to the very old person are also know how to use the internet in any of one of the methods and one of the modes. And now the middle age group, where the young to the 60 to 70 years of the people, where they are more of using this internet in any of the way, either there's a business, or in this their social activities, or in different approaches, even by paying the money to the net banking system or to the apps. So after this pandemic, and the involvement of internet is dramatically increased when you compare before the COVID-19, or the demonetization of the money in India itself. And with this, you can think of how the Western countries and the European countries and the China in far before the India. So this is how internet is used in a 60 seconds. And how the evolution of this internet have been occurred is, so you can think of internet of occurrence before the vacuum tubes or transistors arrivement, and after the transistors or vacuum tubes development. Before the vacuum tube development, nobody thought of defining the communication between a mode of methodology between a device to device, at least. But as the technology in the electronics have been increased, then automatically the communication modes and methodology have been straight away increasing. So before 1948, only the mathematical theory and the communications have been done. But after 1958 or 62, then there is ARPANET based communication of packet switching have been introduced. Then they have made a TCP/IP protocol. IBM have introduced. Then from there, the early of 1990s, World Wide Web has been developed, and the Microsoft have developed the webmail. Thereafter, in era of 2000, we have introduced to Google or the Gmail or many other aspects. So you think before, just think of 1947 to 2020, there's a 70s or 78, around 78 years of independence. We could see only in the last 20 years, there is a lot of changes in the technology have been happened. And day to day, the technology growth, you cannot expect how it is going in the parabolic situation or exponential curve. So with this internet, so what internet is, when we search internet in a Google, or when we communicate with mails, or when we communicate through the chat, this kind of internet is called Internet of People. But what is Internet of Things? What is required for Internet of Things, and why we have to go for Internet of Things? And this we'll see in the next slides. So if I have to define the Internet of Things, Internet of Things can be done by connecting from anywhere, to anyone at any time and any place and any service at any network. So this can be really defined as a current internet, and providing the connections between the communication and the internet networking between the devices and the physical objects. So the physical objects are here maybe the sensors, or the devices, or the things, is a growing trend that is often referred to as the Internet of Things. So the basic requirements for connecting any things or three. Hello.
हेलो
Hello.
ये भी आ रहा है
Hello.
गूगल
Dr. Ganser, is my voice is okay?
हेलो देखो आ रहा है इधर
Hello.
अभी नहीं है कैंसिल खत्म हो गया है ये
Hello.
यार presenting
Hello, participants. Do you have any problem from my side? Are you able to hear?
No, it is
Sir, no problem, and it's audible clearly.
No, but I could hear some noise. That was the reason. Yeah. Thanks a lot.
Okay, sir.
So the basic requirements when I have to connect for any device or anything through the internet is most important thing is you should have a unique identity, and you should be able to communicate. That is called communication ability. That may be with low power communication or high power communication, or through a local area network, or with a WAN, or through some Wi-Fi connectivity, or through a particular protocol. So you might be very familiar with, if you are known to the Internet of Things, the MQTT protocol is much used in connecting the machine-to-machine devices or the Internet of Things. And finally, the thing for the Internet of Things is most important thing is sensors, and which plays a vital role in establishing an Internet of Things or defining an Internet of Things. So how we can see in a real-time situation with respect to in IoT or the intelligent systems when you connected with the world. So here I have chosen 5 particular examples. You can see the first when you see in terms of communication systems. So every person in today's life, but in today, that is a scenario of 2020, each person is connected with minimum 7 devices through the internet. That may be your television, or that may be the mobile, or that may be your workstation at the office, or the laptop, are some of the smart applications at your home or the automotive vector, at least the smart parking or the smart enabling of the car through the smart grid technology. And the most important and the particular IoT technology, I have come across one of the Chennai's medical applications of the hospitals, which they have completely working with IoT. When you even enter into the hospital, the doctor directly will not diagnose you, or you cannot consult the doctor directly. Before that, everything will be connected to the IoT technology, and the robots will be you should consult to the robot, and you should explain your problem to the robot, and based on the situation and what kind of symptoms you have, the robot will allow you to go to or consult the particular specialist. So this, and moreover, all the consultations which will be done through the internet, and all the reports will be admitted into the internet, and to the cloud, everything can be accessed to the doctor. And now in today's during the COVID situation or the after COVID situation, many of the hospitals have been adopting this IoT technology or internet, at least through the cloud, the data. The doctors are the patients have been consulting to the doctors. And how this is managed, or how this is happening, is through the connectivity and managing the remotely monitored or power control devices and the secured data protection. If you see, if your data is not protected, and if your data is not able to retrieve, and here sending the data is not only the thing the internet of technology is required, but also this intelligent system should also able to analyze the data, and you should also able to receive that data too. And most of the people have already experienced the retail market, how the retail markets like Amazon, Flipkart, or Myntra, many of this kind of shopping has been done through the Internet of Things. When you book it with your location through the GPS sensors, everything even Zomato, simple example is Zomato, or the food delivery systems, how they are doing the deliveries at your doorstep. And the industrial growth rate in today's era of Industry 4.0, with IoT and the robotics automation, 30% of annual growth rate is recorded in the industry, with improvisation of IoT into their manufacturing sectors, from the logistics to the delivery of the project. And in 23 and in automotive itself, I can see a growth rate is dramatically increased. In 2010, it was around 8.7 millions of cars were connected to the Internet of Things, or the connected cars were available. In 2016, it was 23.6, and in 2020, it is more than 100 million connected cars were in the globe. And this may increase by 2023 or 2025 exponentially to somewhere like 500 million cars will be connected to through the connected car technology. And if I move forward, what to do this real-time applications of IoT, what exactly I required, the necessity or the necessary information or necessity for IoT in today's human's life. So these 7 points will correlate you whenever you are using some situation through the IoT or the internet. First thing is, like, you are going to control two things. If you think as a customer perspective or a personal perspective in your day-to-day life, you are using the Internet of Things when you jog. The slipper, the shoes sensors, or your variables are sensing the data and processing the data and sending the information to your mobile or your HMI devices, where you can see your pulse rate or your body rate or your different aspects of situation in different aspects what you want to control in the day-to-day life. And if you see in the other aspect in the industry, by sitting at your home, and how you are going to control your platform of supply chain unit, from a production unit to the logistics unit, and how in a simple example, if you take from a logistics, if you have received the logistic, numbering the logistic, barcoding the logistic, and placing in a segregating into the tracks or a trace, and allowing to pick up at any point of time with the unique identity. That unique identity is the first and most important thing when you talk about the IoT. And second part is like improve the resource utilization ratio. See, if any problem has occurred in the production unit and the production bench, the diagnostics are nowadays very easy with this Internet of Things and automation, because you can see where the problem has occurred, how the problem has occurred, and why this problem has occurred, what could it make this problem, and how can we resolve. So this all have been doing through the IoT and analysis and the machine learning algorithms in industry. So this makes the utilization ratio and the you can say the production will not stop for a longer time, and initiating the production will be very easy. Then better relationship between the human and the nature. And if you see the sensing systems or geosensing remote sensing systems, which are sending the weather forecast in the day to day and the nature about the nature, and we could able to predict at what time the rainy season or the rains or what kind of situations are going to happen at nearest to your place based on the weather incidents. And the main thing is intellectual entity. By integrating with the human and the physical systems will be part of it. Then a flexible configuration, and you can flexible configuration is nothing but you can access the data from any place, and you can just work from any place, like as I'm working today from a remote place to my organization or the production unit. And you can have a universal transport and the internet working, and accessibility and the usability can be done to the IoT very easily. So these 7 points are the necessity for bringing the IoT into the human life or the industry. And we will talk about industry more points in my later slides. And what are the key features when I talk about IoT? As I've already discussed, communication or the connectivity is the most important one, and the sensors. Without the sensors, or the accuracy of the sensors is very, very important in making the IoT in distinct manner. Without these sensors, the transformation of data and standardizing the data is very difficult, because when you get the data has to undergo into some kind of analysis. If your data itself is wrong, then the analysis will make you or lead it to wrong directions of predictions. Then all the data which we get as to the passive network, and which will make into the active systems. Then active engagement of the system and the small devices which we may build with the deliver with the precision of and the scalability and the versatility. And the artificial intelligence, more I can say, machine learning techniques are more important in analyzing this data, are predicting the features from this whatever the data which we get from the sensors and the communication. And how the Internet of Things have been evaluating, and what are our goals ideally for many years away. So if I have to see my connecting devices and the collecting the data is in the way we are today or yesterday. But in the next stage, we have to get the access the data and the complex analytics. But the ideal goal is to have a unique value and connect to the your particular analysis, which can predict exactly. So how it is happening? So connectivity and intelligence are part of your connecting the devices from machine to machine. But connecting is not enough to collect the data, but it also should collect the data and it should store. And if you're storing the data at your local area network or your PC, it is not enough. So then to access the data in a simple local area network, it might be enough to connect with the Bluetooth and you can access the data. But finally, our main goal is not only to connect across your 4 or 5 people as a consumer, but in an industry perspective, you can able to access the data at any point of time, from anywhere, and it should be more customer friendly. So this data should be sent to the cloud, and you should have a standardized protocols to access the data and opening APIs, that is apps. And that is with this collecting the data and sending the data and accessing the data is not enough. Then we should able to secure this data. And how you will say, secure this data? And you might have been also encountering people who are working in the microgrids and the smart grids, this making the data more and more secure. The current area of topics which people are working on, cyber systems of power electronics, or cyber systems of automotives, or cyber systems of microgrid and smart grid techniques. So why this cyber systems has been evolved is because this data from the cloud, everybody will be sending the data and accessing the data at different clouds. If you talk a simple data, when you talk in the Amazon or Amazon cloud or Microsoft cloud, it is not only enough. There are a lot of security issues which one should analyze this. How you are going to analyze this? This can be done through the big data analytics, or through or machine learning algorithms. Now the buzz topic is the deep learning algorithms. These are all part of, again, the machine learning techniques, and people says in different methodologies. And whenever you have this, all the four, and for identifying your own data and predicting to a particular cause, or particularly protecting something, then you have to have a realize true potential to the connected society. So that is finally an ideal goal to satisfy the customer by making the Internet of Things part of the Internet of Things. So these are the 5 steps one has to be fixed when you are thinking about the IoT. Then what are the drivers for IoT? I could see these are the when you see as a network, as a platform, and how the technology is transmitting into the business transition. So the technology evaluation is not enough for you to sustain with IoT, because if you want to grow in terms of business, then you should have some business transition from your whatever the technology you develop. So that how it will happen. So whatever the business technology you should develop, you should able to sell, or you should able to market it, and you should able to globalize this, and you should have some kind of innovation in it. Without innovation, there are a lot of startups evolving in today, but only the startups which can sustain in the market with a good innovation in them, and with good business practice, or with good business models, then only you can able to sustain in the market. So you can see from the technology transition, BOYD, that's buy your own device, and may transmit into your own growth and innovation. Then whatever the data you have from your device, then it will be transferred to the cloud, and the new breeds of apps are coming, and the sensors and devices were placed on your own devices, and the big data analytics. So if the circle, if you go from the big data analytics, once you've done the big data analytics, then you should have a security and privacy. If this is happened, then you should able to globalize your business and experience the customer experience. You should get the feedback from the customers, and you should make the feel of customers to make it into the business model, make it into the customer satisfaction. This will lead to a good business model, and which makes you into growth and innovation in the business. So a technology transition can bring into the business transition. Then only any technology in IoT or any business model can sustain in the industry. So these are some of the drivers which makes like growth of innovation, new business models, and experience the expectations of the customers, and the globalization, and security and privacy. These 5 can make you into the technology transmission, or the technology transmission can make into the business transmission. So these are the bidirectional ways one can walk from. So this all will be leading to your own technology, BYOT. So next slide. So in previous slide, we would have seen the necessity of IoT and the drivers of IoT. But how to frame this IoT? So we can only frame the IoT based on a circular fashion. So I cannot, you can see there are 6 points over here, but none of the point with no one, if you remove one of the point, you cannot complete the circle, or you cannot complete the framework. So first thing, if you see from the device connection, when you connect the devices to the machines, you should connect to the device, and how you are going to connect to the device through a protocol, and that protocols I'll be discussing in my later slides, and the embedded intelligence. And once you connect the device, then you should able to capture the data, and you should tag the data with a unique identity, and you should able to store the data at some place. So that may be cloud, and you should able to communicate the data through the networks or the cloud and the edge data transportation system. And after this communication, your path is not ended. Then you should able to analyze this data, as we have discussed, with the big data analysis, or the AI, or the cognitive methodologies, or the deep learning techniques. And you should able to take an actions and the process and the intelligent process intelligence, which makes the human comfortability. Finally, any industry or any person who works for the human values, and the making the human more comfortable with the different experiences. So final stakeholders will be the human being. So this smart applications may make the human lazy, but in today's days, the IoT and the human customer satisfaction for the business is much important, and tangible. That will give the stakeholders and the industries and the customers tangible benefits. So these are device connection, data sensing, communication, and data analytics, and data value and human value are more important in whenever you are framing any problem of IoT. It is not related to a particular problem. If you are making any problem, when you are thinking any research problem, this all 6 points should be considered when you think of IoT to some problem. If you're not even when you think of microgrid, final stakeholder is, or when you think of a smart grid, final stakeholder is a customer. So you should able to satisfy that customer with this IoT. And what are the benefits with IoT is, we can increase the productivity in the production cycle, and you can improve the quality by making time into the market. So why I have made time to market is, if you're not meeting the lead time or the customer expectations, then your business will not sustain, or your business models are not going to sustain in the market. So some of the examples, the recent customer automotive players who can see the startups have come into the market, but the date which they have promised to the customer, they have not made the promise sustain. So the business have been transferred to the other traditional vendors. Then the process automation is also be part of IoT. And when you have implemented this kind of system, your cost will be automatically reduced, because 3% working may done by the 2% or 1% with the IoT, and faster and better decision making using the different prediction algorithms can be done through the IoT. And when you think of simple example, it may not be a part of an IoT, but a simple example I have made, people connecting to the internet. In today's life, most of the people who are connected with, at least during the COVID, people have tested with the oximeters and the sensing the data to the mobiles, and seeing this ECG sensors or the motion sensors, sending those data into the mobile, and accessing their data, and accessing their body pulse rate or the heartbeat through the internet. So this is called people connecting to the things, since they might be connecting directly to the sensors and the variable devices. You can see on the variable device what is your pulse rate, where you have not communicated the data to the any devices. If you have communicated to the devices through some particular mode, then it may be a part of Ethernet of things, or Internet of things, I can say. So when people connecting to the things, that's a part of a simple monitoring of your own connecting sensors. Then what are the major hardware in academia people uses, or the professors or the students uses, are for the hardware in the IoTs? RF modules. Many of the people might be part of it, and for the signal processing or the data sensing and Wi-Fi or Zigbee or the Bluetooth modules. But in industry, if you see, industry is far away from this Wi-Fi or Zigbee or Bluetooth. So no, we in industry also people uses this, but there are the more smart sensors like Stella or Scala 360 degrees camera sensors, or radars are used to get the data for more accuracy, and those data can be transferred at those data can be transferred at 2.4 mega 2.4 gigahertz of frequency, and x times. So the smart variable devices, which includes some of the examples which we use in day-to-day life, are helmets, jewelry, or the watches, or clothing, even backpacks and socks and shoes. So